Welcome back. Today we are going to discuss one of the most popular algorithms under the category of Bayesian learning, and that is the Navy Bayes classifier. It is one of the most practical Bayesian learning method. When we can make use of this algorithm? Very first thing, if we are having moderate or large training set available with us, we may go with this algorithm. And secondly, if the attributes or the features that describe the instances in the data set are independent of one another, and if each attribute has equal contribution, then we may go with Navy Bayes classifier. So let me focus upon the second condition once again. Attributes or features that describe the instances in the data set are independent of one another, and each attribute has equal contribution in producing the outcome. So to clarify these two conditions, let us see one example. So once again, we are referring to the example that we have seen earlier while discussing decision trees. So this example consists of 4 attributes or 4 independent variables: outlook, temperature, humidity and windy, and the dependent variable is play tennis. So this is the problem that provides us 4 weather conditions and tries to determine or tries to predict whether to play tennis or not. So with relation to this data set, I am going to illustrate these 2 conditions. Features are independent and every attribute has equal contribution. So we assume that no pair of features are dependent on one another. For example, the temperature being hot has nothing to do with the humidity, or the outlook being rainy has no effect on winds. Hence, the features are assumed to be independent. Secondly, each feature is given the same weight or the same importance. For example, knowing only temperature and humidity alone can't predict the outcome accurately. So none of the attributes is irrelevant and assumed to be contributing equally to produce the outcome. Though this algorithm is being widely used in the domain of machine learning, I am listing here 2 of the applications of this algorithm. The first is, this algorithm is popularly being used for medical diagnosis problems, and secondly, this algorithm is being used to classify text documents. As I mentioned, these are only the few applications. We are having enormous list of applications. Those are actually making use of this Navy Bayes classifier. Let us go through the detailed description of Navy Bayes classifier. Let us assume that we have a target function f which accepts the instance set x and produces the outcome as y, where each instance x is described by attributes x1, x2, x3 up to xm. So we are talking about a classification problem wherein we have provided with the data set in which we are having the instances like X. Every instance is being described with m number of attributes, and we would like to build a classifier that will classify the instances with some label. So y corresponds to a set of labels or the predicted values. Ultimately, what we are expecting is our classifier should give us a class label for a new sample or new instance presented to this classifier. The Bayesian approach to classifying the new instance is to assign the most probable target value, denoted here as y map, given the attribute values x1, x2, x3 up to xm. These values are actually describing that new instance. So formally we can write the expression as y map is equal to argmax over yi's, those belongs to capital Y, of probability of yj given x1, x2, x3 up to xm. How to interpret this expression? We would like to find out the probability of given set of input or data for all possible values of the class variable y and pick up the output with maximum probability. Now here we are going to make use of Bayes theorem. We have studied Bayes theorem earlier and we know how to write the expression for Bayes theorem. So Bayes theorem is given as probability of H given D is equal to probability of D given H into probability of H divided by probability of D. Now let us try to modify or rewrite this Bayes theorem using the notations those we are using in this present example. So here in the present example, our hypothesis is nothing but y, that is giving us the target label, and our data is the instance, that is x. So we can replace h and d by y and x respectively, and we can rewrite our Bayes theorem as probability of y given x is equal to probability of x given y into probability of y divided by probability of x. Using this Bayes theorem now, we are going to rewrite our expression for y map. So what we are trying to do here is, now we are replacing our x by the vector x1, x2 up to xm. So now our expression will become as shown here on this slide. Y map is equal to argmax over yj, that belongs to capital Y, probability of x1, x2 up to xm given yj into probability of yj divided by probability of x1, x2 up to xm. As we did earlier, as the denominator in this expression is independent of the hypothesis, we may omit that and we can write y map is equal to argmax over yj, that belongs to y, probability of x1, x2 up to xm given yj into probability of yj. As we can see in this expression, we need to estimate now two terms, probability of x1, x2 up to xm given yj for every yj and probability of yj based on the training data that is provided. It is actually easy to estimate each of the probabilities for yj. How? We can simply count the frequency with which each target value yj appears in the training data, and that will provide us the probability of yj. However, estimating the different probabilities for x1, x2 up to xm given yj, these terms or computation of these terms is not feasible unless we have a very large set of training data. The problem is that the number of these terms is equal to the number of possible instances times the number of possible target values. Therefore, we need to see every instance in the instance space many times in order to obtain the reliable estimates. Now let us refer to our assumptions that we made at the beginning. The Navy Bayes classifier is based on the simplifying assumption that the attribute values are conditionally independent given the target value. In other words, the assumption is that given the target value of the instance, the probability of observing the conjunction x1, x2 up to xm is simply the product of the probabilities for the individual attributes. So let me once again repeat this. The probability of observing the conjunction x1, x2 up to xm can just be seen, or it can be represented as the product of the probabilities for the individual attributes. Thus, we can have the expression like this: probability of x1, x2 up to xm given yj is equal to the product over I equal to 1 to m, that means the number of attributes describing our instance. So, product over I equal to 1 to m probability of xi given yj. By simply substituting this expression now in our earlier y map, we come up with the formal expression for Navy Bayes classifier, and that is denoted as YNB is equal to ARG max over Yj, that belongs to capital Y, probability of Yj into product of probabilities xi given yj, where I is from 1 to m. Here this YNB denotes the target value or the label, that is the output by the Navy Bayes classifier. Now please notice that in Navy Bayes classifier, the number of distinct probability values, that is probability of xi given yj terms, that must be estimated from the training data is now just the number of distinct attribute values times the number of distinct target values. So that is, if we are having m number of attributes, then the terms that we are estimating from the training data, or the number of times we need to do this calculation, is just the number of distinct attribute values, means m times the number of distinct target values. So obviously this number is much smaller number than we saw earlier computation meant for Y map. So let me summarize now. The Navy based learning method uses number 1, a learning step in which the various probabilities of yj and probabilities of xi given yj terms are estimated based on their frequencies over the training data. Number 2, the set of these estimates corresponds to the learned hypothesis. And number 3, this hypothesis is then used to classify each new instance by applying the rule denoted as Navy Bayes classifier. It is important to see the difference between Navy Bayes learning method and other learning methods that we have studied so far. That in Navy Bayes learning method, there is no explicit search through the space of possible hypotheses. Instead, the hypothesis is formed without searching by simply counting the frequency of various data combinations within the training examples. That's all. Now, in this slide, I have tried to simplify our Navy Bayes algorithm as far as practical implementation is considered. So practically, if we would like to use this algorithm for classification, we are having two important steps. Number 1, the learning phase or the learning step, and number 2, the classification step. In learning step, we need to estimate probability of yj and probability of xi given yj. So we need to estimate probability of xi given yj for yj number of times. So we are having two nested for loops here. For each target value yj, estimate probability of yj. For each attribute value xi of each attribute, estimate probability of xi given yj. So after doing this, we will be getting our classifier or learned classifier. Next, we would like to classify a new instance x. So we will be using our Navy Bayes classifier expression ynb equal to arg max over yj that belongs to capital Y, probability of yj into product of probabilities of xi given yj for all xi's in my instance space x. Now let us try to solve one problem. We are using the same training data that we had used earlier for solving a problem under decision tree classifier. So we are having here the data. Have a look. We are having 4 attributes or features: outlook, temperature, humidity and windy, and play tennis is the target variable, which is a dependent variable for which we would like to predict the value yes or no. We have been provided with 14 instances in this training data set, and we are asked to predict for a new instance. The new instance here is denoted as today with 4 values. Outlook is sunny, temperature is hot, humidity is normal and windy is weak. So with this instance we would like to predict whether one should play tennis or not on this day. We are going to solve this problem using Navy based classifier. So we need to find out probability of xi given yj for each xi in capital X and yj in y. To interpret probability of x given y, let us consider one example. So consider the first instance in the given data set where x is having 4 values: sunny, hot, high and weak, and for this instance the y value is no. So how do we interpret probability of x given y for this particular instance? So probability of x given y can be interpreted as probability of not playing tennis given that weather conditions are sunny outlook, temperature hot, high humidity and weak wind. To proceed further with the solution, what we are supposed to compute now? For each feature or for each attribute and for each distinct value of the attribute, we need to estimate probability of xi given yj. And what does this mean? This means that if my feature, say for example outlook is one of the features, so for outlook we are having 3 distinct values: sunny, overcast and rainy. So we need to find out the probability for outlook for all these 3 values given the class labels. Also we need to compute for each target value the probability of yj. This will provide us the class probabilities. Now look at this slide wherein we have tabulated all the results. So let us assume now the first attribute, that is outlook. For outlook we are having 3 distinct values: sunny, overcast and rainy. So what are those columns? We are having the columns yes, no, probability of yes and probability of no. So in this particular cell where we are having sunny and yes, the value is 2. So how do we compute this value 2 now? So let us refer to the data set with 14 number of instances in which we are having 5 samples for which outlook attribute has value sunny. Out of those 5 instances, if we look at the play tennis attribute, 2 instances are having the value of play tennis as yes, and for 3 instances the value of play tennis is no, and that is why we are having here the value 2 for sunny yes and the value 3 for no. Further, we have computed now the probabilities for VJs. Here my VJ values are yes and no. So probability for yes and probability of no. So if once again we look at the training data set, we are having 14 instances, out of which 9 instances are having play tennis value as yes and 5 instances are having play tennis value as no. So for outlook sunny, the probability of yes is 2 divided by 9, meaning we are having 2 instances for which outlook value is sunny and play tennis value is yes, out of total yes instances 9. So probability of yes is 2 divided by 9. Similarly, probability of no is 3 divided by 5. So total no instances are 5 and out of sunny instances we are having 3 sunny instances for which the value of play tennis is no. So probability of no for sunny is 3 divided by 5. Similarly, we can compute for overcast. For overcast, we are having 4 yes values and 0 no value. So probability of yes is 4 divided by 9 and probability of no is 0 divided by 5. For attribute value rainy, we are having 3 yes and 2 no's. So probability of yes for rainy is 3 divided by 9 and probability of no for rainy is 2 divided by 5. So please see here, if we sum up the values in column yes, it comes out to be 9. That means we are summing up the number of instances for which we are having yes value. So overall 9 instances, and similarly the sum of column no is 5, meaning the total number of instances for which play tennis value is no. I hope you must have understood how we have computed these values for attribute outlook. Similarly, we can compute the probability values for attribute temperature and 3 distinct values of temperature: hot, mild and cool. Also for attribute humidity, we are having 2 distinct values, high and normal, and we have computed the probabilities for both of these distinct values. For attribute wind, we are having 2 distinct values, so we have computed the probabilities for these 2 distinct values of wind. So this is how we have computed probabilities for each feature and for each distinct value of that feature. Now the second computation that we would like to have is, we want to find out the class probabilities. So at the right hand side we are having one table that denotes class probabilities. So what we have in this table, we are having a column play tennis with 2 distinct values, yes and no. Total number of instances for play tennis yes are 9 and play tennis no are 5. So probability of yes is 9 divided by 14 and probability of no is 5 divided by 14. Now once again I would like to explain what we mean by these probabilities. So once again, let us consider one example here. In the humidity table, we are having the cell, that is the intersection of normal and probability of yes, and in this cell we are having the probability that we have computed 6 divided by 9. So how we are going to interpret now this probability 6 divided by 9? So this is probability of normal humidity given tennis played, and it is denoted like this: probability of humidity equal to normal given play tennis equal to yes, and this is equal to 6 divided by 9. So I hope you must have understood how we have computed all these probabilities. Let us once again go through these tables showing the probabilities for each attribute and for each attribute value for every distinct value of the target play tennis. Now we have done with the computations. So let us see what has been asked for. If new instance today is given with 4 values: sunny, hot, normal and weak, then predict whether one should play tennis or not. As we know, Navy base classifier is given as YNB is equal to ARG max over YJ, that belongs to capital Y, probability of YJ into probabilities of Xi given Yj, computed all the products for m number of attributes in our instance. So given this formula, now we are rewriting this formula as YNB is equal to ARG max over Yj belongs to capital Y, probability of Yj into probability of x1 given Yj into probability of x2 given Yj into probability of x3 given Yj into probability of x4 given Yj. So this expression is simply the extension of our generic formula. As here we are having m equal to 4, we are having 4 attributes, so we have expanded this original expression of YNB using individual terms for 4 different attributes. Now probability of playing tennis and probability of not playing tennis, that is what we are supposed to find. So let us find out probability of yes given today, that is probability of playing tennis given the instance today, and that is equal to probability of yes into probability of outlook equal to sunny given yes into probability of temperature equal to hot given yes into probability of humidity equal to normal given yes and probability of wind equal to weak given yes. So actually this is computed as the product of the probabilities of all the attributes for given values of today given yes multiplied by probability of yes. Similarly, we can compute probability of not playing tennis. So probability of not playing tennis given the instance today is computed as the product of probabilities for all the attributes having the provided values of the instance given no multiplied by probability of no. So, probability of no given today is equal to probability of no into probability of outlook equal to sunny given no, probability of temperature equal to hot given no, into probability of humidity equal to normal given no, into probability that wind is weak given no. We are done with computation of probabilities in various cases, and also we are done with formulating the solution in terms of the required expressions. So, what has been asked for? If new instance today is given as the attribute values sunny, hot, normal and weak, predict whether one should play tennis or not. Now, let us reproduce two expressions that we have found out: probability of playing tennis and the expression for probability of not playing tennis. That is the probability of yes given today and probability of no given today. So, look at these two expressions once again. We are having computed all those values of the probabilities. So, simply what we are going to do next is we are going to substitute the computed values in these two formulae. So, once again refer to whatever we have computed. So, we are having in the tabular format the probabilities for 4 attributes: outlook, temperature, humidity and wind, and these probabilities are being computed for all distinct values of every attribute. Also, we are having the class probabilities. Now, let us substitute these values as required in computation of probability of playing tennis. So, probability of yes given today can be computed as probability of yes. The probability of yes is 9 divided by 14. So, substitute this into probability of outlook equal to sunny given yes. So, probability of outlook equal to sunny given yes is 2 divided by 9 into probability of temperature equal to hot given yes. Once again it is 2 divided by 9 into probability of humidity equal to normal given yes. Refer to the table, it is equal to 6 divided by 9 into probability of wind equal to weak given yes. It is equal to 6 divided by 9. So, it comes out to be approximately 0.0141. Similarly, we can substitute the values to compute probability of not playing tennis. So, probability of no given today is equal to, by substituting the values, 5 divided by 14, that is the probability of no, into 3 divided by 5 into 2 divided by 5 into 1 divided by 5 into 2 divided by 5. Please refer to the computed values, and the computation comes out to be approximately 0.0068. So, whatever we have computed are the approximate values. Now, to come up with the sound prediction of probabilities for probability of playing tennis and probability of not playing tennis, the next step that we are going to perform is the normalization. Since probability of playing tennis given the instance today plus probability of not playing tennis given the instance today is equal to 1, we may use the following formula to normalize our earlier result. So probability of yes given today is equal to 0.0141 divided by 0.0141 plus 0.0068, that comes out to be 0.67, and probability of not playing tennis given the instance today is equal to probability of not playing tennis given today divided by probability of playing tennis given today plus probability of not playing tennis given today. So this is the normalization, and substituting the values, it comes out to be 0.33. That means probability of playing tennis today is equal to 67% and probability of not playing tennis today is equal to 33%. So obviously probability of playing tennis today is greater than probability of not playing tennis today. So by comparing these probabilities, finally we may predict that tennis would be played today. That means prediction that tennis would be played is yes. So I hope you must have understood whatever we have done. Once again go through all the steps and further, based on the same data and same computation, try to find out or try to predict one more instance. So this is the exercise for you. Use the same training data, and if the new instance day is equal to sunny, cool, high and strong, predict whether one should play tennis or not. So this is just for the practice, and I hope you can find out the answer for the question. Now let us have a look at some important points to be noted regarding Navy Bayes algorithm. Number 1, we assumed while defining Navy Bayes algorithm that the attributes should be conditionally independent of one another. This assumption made by Navy Bayes is typically not correct in real world situations, or the conditional independence assumption is often violated in real world situations. In fact, the independence assumption is never correct but often surprisingly works well in practice. The second point is related to estimating probabilities. Up to this point, we have estimated probabilities by the fraction of times the event is observed to occur over the total number of opportunities. While this fraction or the estimate provides a good estimate of the probability in many cases, it provides poor estimates when NC is 0 or very small. For example, in our problem of having the weather conditions and the prediction for whether to play tennis or not, there is no instance with target value play tennis equal to no that has outlook value overcast. This implies that probability of outlook equal to overcast given no is equal to 0, and hence probability of no given today becomes 0. The typical solution is the Bayesian estimate for probability, or it is also known as M estimate of probability, and is given as probability of xi given yj is nc plus mp divided by n plus m, where n is number of training examples for which y is equal to yj, nc is number of examples for which y equal to yj and x equal to xi, p is prior estimate for probability of xi given yj, and m is weight given to prior, that is number of virtual examples. The small m and the capital M that we used earlier are totally different. We have used capital M for denoting number of attributes describing the instance, and the small m is weight given to prior, that is the number of virtual examples. And with this we conclude our discussion regarding Navy Bayes classifier. Thank you.